Hello. Good afternoon, everyone. We'll start the session on AI and computational geomechanics. Our chair of the session will be Raghuvi Rao Pallepatti and co-chair will be Engineer Govindraj. Our thematic speaker is Dr. Piju Shamui. I would like to request chair of the session to introduce our thematic speaker.
Good afternoon. First, let me thank the organizers for giving us this opportunity. So, in this session of AI and computational geomechanics, presentation and multiple paper presentations. Now, I'll introduce the theme speaker of this session, Professor Piju Somai. He is a professor at National Institute of Technology, Patna. Piju Somai has research expertise includes soil liquefaction, lateral spreading, reliability and risk analysis, artificial intelligence, disaster mitigation, and site characterization. Dr. Somai has received several awards of excellence in research and teaching, including IIT Roorkee Shamsher Prakash Research Award, IGS Sardar Resham Singh Memorial Award, IACMAG Excellent Regional Contributions Award. He is a fellow of Indian Society of Earthquake Technology, and he is a guest professor at University of Science and Technology, Beijing. He is also has a title of docent at Tampere University. He was adjunct professor at Ton Duc Thong University, Vietnam. Now may I request Professor Somai to deliver his talk. Is it possible to switch off that floodlights?
Yeah. Okay, very good afternoon. And thank you, my teacher, Professor Raghuvi Rao and that Govind, for your kind words. And so, in this lectures, I think I will try to tell about that what is the progress of the AI so far till today, and what about the problems we are facing nowadays when you are using the AI. So, if you see that our content actually, that application of the large language model, this is a very newly advanced technique of the AI, but why large language model is required, that also I will tell in this lecture. And then will be some of the concept of the hybrid AI, means how traditional AI is sometimes giving problem. So how we can, this problem can be solved by the using hybrid AI approach. And last is the some conclusion and some take-home message for the young researcher and who is working on this field. So coming back to the application, if you look at, generally AI has been started long back, but recently myself as in Samui 2008, I have tried to develop site characterization model of the Bangalore city, that is in 2008. Next, liquefaction, prediction of the soil liquefaction is also done by Gandham et al. In 2013, he has used descent trees. Descent trees means based on some parameter, you will classify whether soil will liquefy or non-liquefy. So that is another very well-establishment technique, and he has got some good encouraging result also when he applied the descent trees for the liquefaction problem. And recently, 2024, energy pile also, the design of the energy pile has been done by using AI. And energy pile, actually, we know that nowadays is very useful for the net zero emission, and that is the sources of the one renewable energy. So by using energy pile, what we can do, we can heating our building during the winter time, and during the summer time, we can take the heat from the building, and so that the cost of the electricity will reduce. So in that designing of the energy pile by also done by the AI model. Next, in the tunneling, actually tunneling is a very challenging task, and if you see that in India is going for a lot of tunneling, and there actually crack is another issue, how to develop the crack and all these. By image processing by the AI, they are doing. But still today, this all problem actually, everything is all right, good. But the problem is that in AI actually, when we are giving that as an input, that we have given as a data set. For example, if we give as an input the soil angle of friction, so you will give not soil angle of friction, you will give only 32 degree. Similarly, your cohesion is also 30. So if you take the height of the slope is 12. So you are not giving the computer that what actually exactly meaning. That means whether 30 and 32 and 12, that is what is it actually? Computer does not know that what is this thing. So that's why the problem arising, and that's why they are dealing with something else. Means for example, your SPD data, it can be never be negative. So if you tell the computer the SPD value is 25, and that will be as an input. So that's why actually your large language model is coming to the pictures. So if you look at the AI, actually we are giving the input 20.3, 10, 35, 40, 4.7, and 0.25. If you show this data set, if he does not know anything about the civil engineering, he will never understand what is 20.3, what is 10, what is 35, and what is 40. So he will never understand. But in large language model, if you look at, they will give unit weight. So computer will lead, this is as a unit weight is 20.3, cohesion is 10, internal friction angle is 35, slope angle is 40, slope height is 4.7, and pore water pressure ratio is 0.25. So this will feed to the model, and model will tell that whether it is stable or failure. So that is the advantage we are getting by using large language model. So AI, so far the AI, whatever you are using now, everything they are using as a data set. Means they are not anything, they are not in classifying whether soil cohesion or soil internal friction or the soil unit weight. Now, what is the AI actually? LLM. LLM is basically nothing but a neural network, but designed to understand, generate, and respond to the human-like text. That means, as we are talking, for example, that if our soil value, soil ka gamma is this one, and our earthquake magnitude is 7.5, and peak ground acceleration is this one, then I want to know that what will be whether soil will be liquefy or not liquefy. So I will give the input to the computer that my angle of soil unit weight is this one, and peak ground acceleration is this one, earthquake magnitude is this one. Then the model will tell that whether soil will liquefy or not liquefy. So that means we can give as a text as an input into this model. So that's why it's better than the AI model. Next, it is pretend on the extensive internet data and comprise billions of parameters and enable powerful capability in general purpose language understanding and generation. That means if you use the data set, automatically your problem will be more complicated, and it will be very much computationally demanding. So a lot of parameters is involved, not like very easy to develop. Last point is that LLM is rely on the transformer architecture. That means you have to transform. So, for example, you cannot give as an input, because then mathematical calculation is not possible. So always we will use some transformer architecture, and that depends on the deep neural network architecture. So what is I have taken one example of the slope problem. So there's a huge amount of data set is there of the slope data set. That is, there are various parameters, your gamma, C, phi, and slope angle, and height, and pore water pressure ratio. And if you can see, the status is your failure or stable or all these things. So that means if you look at, this is basically one stability of the slope problem, and this is all input, and output will be your two case, whether slope will be stable or it will be failed. So when you are using this data set as a input of a large language model, then we will give some text embedding model. So text embedding model, what they will do, they will they will take as the input as a values. So this is the basic steps of the large language model. So what is the architecture of the large language model? So first, the final GPT architecture, if you see that is the first is the transformer block, and then layer normalization, that is very important. And next is the JLU activation function, that is same like neural network, and feed forward neural network, that is simple neural network and shortcut connection. So here actually, if you see that data set, we have divided into three parts: training, testing, and validation. So we have used around 268 data set as a training data set, and testing data set 78, and validation is 39. So training means you have to train the model, means we are fixing the parameter of the various parameter to give the good result. And validation means we'll check that whether our training is going good way or bad way. So whether we are forcing the model to give the good result. And testing is to verify the developed model. When the model is developed, to check that how is the performance of the model. So if you think the layer normalization is very important stacks, if you see that, so we are giving the layer input around as 5 values we are giving as a input, and after doing the layer output, if you see that the mean value is 0.13 and variance is 0.39, so we want to make the normalization between mean 0 and variance 1. So always the data normalization is very important in AI technique. So I have used here actually mean 0, and we want to make the normalization of the variance 1. So based on that, we normalize the data set here. So next is if you see that out of box, what is happening inside the box. So if you give that, so here is the input, and then tokenized a text, and token encoding layers, and then dropout, and layer norm 1, the shortcut, and then transformer is using the Marx multi-based model, and dropout again, and layer normalization. So if you look at, in this actually, there's a huge number of hidden layer has been used. If you see the traditional neural network, there is only 2 or 3 hidden layer, but here actually huge number of hidden layer is used. So it will take a lot of time to run the code. The LLM required very powerful computer to run this, for developing the model. So if you see the training out of LLM, so if you look at that, there is 2 types of loss. There are training and validation loss. So up to gone, I have went to up to 30 epochs. So because after 30 epochs, if you look at, there is a gap is increasing between the training loss and validation loss. So I have stopped the model at 30 loss after 30, because if you go beyond 30, then there is a chance of overfitting or overtraining can occur. So I have gone only 30 epochs, and then I have stopped the model. Now coming to the accuracy of the model, so first one is the confusion matrix I have developed. So there is confusion matrix means there is 2 things. One is the positive and negative. Positive means if your slope is stable, then it is a positive condition, and your slope is failed, then it's a negative condition. That means this is the actual level in the x-axis, and your predicted level is the what model is giving. So when is your positive, for example, your slope is positive, but model is giving negative, then it will come to this blue zone. But when your actual level is negative and your model is also giving negative, then it will come with the red zone. So similarly, if you see that this is for the training data set, so this is for the positive and negative data set, and this is for the validation data set, and this is for the testing data set. So this is overall actually one of the, by using these things, you can judge the model, whether model is good or bad. But there are some other parameters also there. That is actually accuracy, that is the true positive and true negative, plus true positive plus true negative plus false positive plus false negative. That means true positive means when your model is giving positive, model result is positive and your actual is also positive, then true positive. And false positive means when your model result is negative, but your actual result is the positive. Similarly, false negative means when actual result is negative, but your model is giving the positive result. So accuracy is calculated TP plus TN divided by the TP plus TN plus FN plus AP. So when if it is a good model, then it will be close to the 100%. So then another parameter is there, that is called a precision, that is true positive divided by the true positive plus false positive. Recall is a true positive plus false negative, and F1 score is the 2 into precision into recall by the precision plus recall. So this is the all parameter that to judge the LLM model. This is just like AI. Also, we have used the same parameters. Here also using the same parameter. So now, next, my second talk is the concept of the hybrid AI. If you look at that, generally, if you see that all traditional AI, what they're doing, they try to minimize the error, actually. So minimization error means what is the error you record? You record the error is equal to 0. But when you are minimizing some function, that minimum value can be anything. For example, it can be 0, it can be -1, it can be -2, -3, -4, it will go on. But I am interested only in the zero things. So when you are applying the traditional optimization technique, that time sometimes it can go up to any point. So you will get the minimum value maybe 5, -5, -6. That is also a minimum value. But I am interested only when the error will be 0. That is my goal. So that's why what is the traditional AI is there, and if you apply the meta-heuristic optimization technique, that means where in meta-heuristic optimization technique, you can tell the model this is your optimum solution. So optimum solution means my error should be close to 0. So you can define itself into the model that my optimal solution is 0, and you should try to achieve this. So that's why it can give the better result when compared to the traditional AI model. So there is a various optimization, meta-heuristic optimization technique is there. If you look at, there is something is the human-based, swarm intelligence, evolutionary algorithm, and physics-based. Human-based is the group search optimizer, harmony search, imperialist competitive algorithm, language championship algorithm, Socratic competition. There's plenty of algorithm is available. Swarm intelligence and colony optimization, artificial bee colony, and line optimizer. The one thing is, I want to tell you that every model has some drawbacks actually. Every model has some limitations, some advantage as well as some disadvantages. So in a particular problem, I cannot tell that this is the best model and you use for problem. So you have to check for your problem and which model you can use it. So that is a big problem when you are using a meta-heuristic optimization model, just like AI model. So there is no universal truth that you use and colony optimization for every geotechnical problem. No, we cannot tell that. So we have to check that which model is giving the better result for a particular problem. So that's why the next question is very important. I think I'll just take 2 minutes. Yeah, so these two questions is very important when you are using AI model for a given type of problem. So if you take a type of problem, for example, you want to predict soil liquefaction, slope stability, or pile capacity, or anything, what is the best algorithm to use? So whatever the best algorithm to use. And second is for a given algorithm, if somebody is giving the algorithm, so what kind of problem can it solve? These two questions is very much important when you are using a meta-heuristic optimization technique. So I am almost closing. Before going, some take-home message that in India, in an Industry 4 context, if you heard that, data set is very important nowadays. When you are taking any decision, so you take the data set for the various sources, production equipment system, as well as customer management system. So AI can be used, take a very lead role, because if you want to handle many data sets, so AI can be very useful. But my caution is that when challenge such as ethical consideration, as well as digital divide and security and compliance issue must be addressed to ensure the responsible and equitable deployment of the AI solution. So that means you cannot 100% believe on the AI solution. Ultimately, you have to think that which solution will take it. That is my ultimate conclusion. So thank you for your kind attention. This is some of the books. It is available in my Amazon author page also. The LCBR as well as in the Fincher book. Thank you, and questions are welcome. And if you want to ask the question later also, or any collaboration, you can call me and you can email me also. Thank you. Thanks a lot to the organizer.
Thank you very much, Professor Samay. Actually, he has given nice explanation about the slope stability and then hybrid AI problems. And the very nice thing is he has given you a take-home message. Thank you very much.
Thank you, sir.
Now, I would like to request our chair and co-chair to hand over token of appreciation to Dr. Sam.
we have paper presentations. May I know who are all present? Advancing liquefaction. Who is present? Hello? Advancing liquefaction susceptibility assessment with machine learning on cyclic triaxial test data. Anybody present? Yeah, okay. Please introduce yourself and then start.
Total 8 participants are there, so maximum some 7 minutes for each participant.
Thank you, sir. Hello, everyone. As it is the last day of the conference, and I believe everyone must be exhausted, so I'll try to finish my presentation in very brief time. Firstly, I'll introduce myself. Myself, Sweta Shah, currently working as apprentice postgraduate engineer in Tunnel and Ground Engineering Department at Jacobs Solution.
Can you please increase the volume? Control room.
Hello? Okay. So myself, Sweta Shah. Currently, I am working as apprentice postgraduate engineer at Jacobs Solution, Hyderabad, India. This research is a part of my master's project, which I conducted with the help of PhD scholar Vaishnavi Verde under the guidance of Professor Umasankar Balunaini. And my research title is Advancing Liquefaction Susceptibility Assessment with Machine Learning on Cyclic Triaxial Test Data. So these are the contents of my slide. So firstly, I'll go with introduction, the literature review, and we will discuss objectives, data set, the models that I considered, and then we will come to results, discussion, and conclusion. So firstly, going with the definition of liquefaction, it occurs in loose sandy soil whenever huge amount of load is subjected in a very short period of time, just like earthquake or volcanic eruption. Whenever liquefaction occurs, the soil loses its shear strength because of increase in pore water pressure and then behaves like liquid. So effective stress reduces, strength also reduces, stiffness reduces, and deformation rapidly increases. The figure there is one of the post effect called sand boils in liquefaction occurred due to California earthquake in 1979. So, as a geotechnical engineer, we must be well aware of the methods how to assess this liquefaction potential. So, traditionally speaking, there is a method called stress-based method developed by Sid and Idris in 1967, which had undergone a lot of advancement in these years. So basically, in this method, we assess liquefaction potential by computing factor of safety against liquefaction, which is nothing but a ratio of CRR to CSR. CRR is the resistance, CSR is the load that occurs because of earthquake that can be calculated with the formula given here. So, for this CRR, we have various empirical relations which are usually in situ tests like SPT, CPT, or shear wave velocity based. So, what we are trying to do in this research is, we are trying to use ML models so that we can predict the CRR, but our base will be cyclic triaxial test. Because mostly we are relying on the SPT and CPT test data which are generic to a particular site and not generally applicable to all kind of problems. So we are trying to use in cyclic triaxial test data to develop a model to predict CRR that can be used for factor of safety against liquefaction computation. So for this, in ML algorithms, I did some literature research, and what key points I found out are some algorithms such as ANN, Bayesian network, support vector machine, they have been gradually developed in the field of geotechnical engineering, and these algorithms singly they are not able to consider all soil properties when we are building a model, but when we combine one or two models, then we are easily we are easily able to develop this soil model. So, in this study, we are going ahead with this multiple models combination called ensemble-based approach, where more than one hypothesis will be considered so that it gives better result. Therefore, ensemble-based models are considered in this research. So, the objectives of my presentation are, firstly, I'll check applicability of the ML models, mostly ensemble-based models, for the prediction of CRR on cyclic triaxial test data. Then after, I'll apply these results on some case studies to see whether the predicted results, how they are performing in the unseen data. Then we will see the sensitive parameters affecting CRR, and then the case study validations are there. So the data sets that I considered, as I mentioned, it is cyclic triaxial test data. These data are collected from 12 different published studies, and I considered the input parameters which are shown in this correlation matrix table. So fines content, relative density, mean particle size, number of cycles, coefficient of uniformity, minimum maximum void ratio, and effective overburden pressure. These are the input parameters for my ML model, and the output parameter will be CRR. So from these 12 studies, I have collected total 638 data points, and among these 638 data points, 80% of data will be training data, and 20% will be the testing data. So when I am considering these 4 ensemble-based models. So briefly, I'll just discuss what these models are, and then we will go to the results. So starting with the bagging regressor. So just think bagging as it considers multiple regressors and then averages all the result. So simply, it is averaging different samples and then giving us the average predicted value. Now, random forest, it is also same like bagging regressor, just in the sample some randomization will be created. For these both in symbol-based models, decision tree is the base model. Now, thereafter extra tree. In extra tree, some more threshold will be there in random, like in random forest, and this is other is the gradient boosting, where other not simply averaging, but some weights will be added, and then weighted average will be the total finally obtained CRR value. So these 4 models I have used in the 638 cyclic triaxial test data points, and the results I obtained can be seen in this table. As in the earlier thematic lecture, we already observed some basic performance metrics. So I'm not going in detail with what these performance metrics are. Just to understand, the R square and adjusted R square are the measurement of accuracy. Higher the R square or adjusted R square, better the model. RMSE and MAE are the error matrices. The lesser they are, the better the model is. So based on the result that I obtained, what we can see is random forest is somewhat better than the other 3 models in this 638 data points. And these all results are on the test data. We always talk results on test data only. So once, okay, we understood what performance we obtained in test data. Now we will see what parameters among the collected input parameters were most sensitive parameters to CRR. So for this, we are conducting this sensitivity analysis. So sensitivity analysis is okay. So from this sensitivity analysis, what we understand is that DR, D50, and FC are found to be most influential to CRR. And then we are conducting case studies, and we conducted total 4 case studies, 3 from Italy and 1 from Japan. And overall, we can see the verdict that we obtained from ML and the verdict that is reported in the papers are matching. So for this study, it is good, we can say, for the case studies. So finally, I'd like to conclude my presentation. So we collected 630 data points. We used 4 models, and we obtained that RF performed best. Then we conduct some case studies, and then we found out that it was somewhat agreeing with the already published result. And one thing we like to note is that it is completely black box model. So suppose instead of this data point, we consider some other data points, some variations might occur. So one has to be careful about that whenever they are working with ML. Now, these are the references. And lastly, I'd like to talk about my company, Jacobs, who sponsored here so that I can come here and present my work. So some of our international projects include high-speed rail in UK, Marine View Drive Highway project in USA, major works in Saudi Arabia like NEOM IPC modules and NEOM Vault. And we are also doing domestic projects like New Ganga Bridge, major airport projects like NMIL, BIL, and Hyderabad Metro dedicated freight corridor, as well as some industrial and greenfield airport development projects. So I would like to thank my company that because of it, I came here and present my academic work in front of all of you. And thank you. If any questions are there, I'm happy to answer.
Thank you very much. I think questions we can talk later because now running short of time. So may I call the next presenter, prediction of input parameters for design of flexible payments of clay soil using optimized machine learning techniques. Anybody present? So the next one is predicting the payment condition using ultrasonic pulse velocity and AI techniques.
Good afternoon to one and all present here. My today's discussions dwell into the subject of predicting. Yes, I'm Dr. Jigisha Vashi. I am from Narsimonji Institute, and this particular presentation, my students supposed to present, but at the last moment, due to some unavoidable circumstances, he was not able to present it, so I'm presenting it. So my today's discussions dwell into the subject of predicting payment conditions using ultrasonic pulse velocity and some AI technique. So these are the following contents for today's discussions, which will be seen in the subsequent slides. We know that in India, road are the major mode of transport, which covers about 87% of the passenger traffic and 60% of the goods traffic, which carrying a huge government investment in budget, approximately 31,000 crores in 14-15 to 3 lakhs crores in 24-25 in expenses. So in this particularly rapid growth condition in India, to evaluate the payment condition accurately is a need of ours. So we are aware that we have rigid payment, flexible payment, and semi-rigid payments, considering the various layers of the surface, course, base course, sub-base course. Particularly the payment failures start from the subgrades, and which make it critical to the analysis of the payment conditions. So we have the traditional methods which can predict the payment parameters like CBR, subgrade modulus, etc. And always it gives the realistic values because of the variability in the soil conditions. So to overcome this, ultrasonic pulse velocity test can be a good test to assess the payment conditions. So for this studies, 400-meter stretch in the Dhule district of Maharashtra were considered in the Sirpur regions where the soil samples were collected from the depth of 0.5 meter below the road surface. And considering the 3 point, one is at the beginning of the stretch, one is at the middle of the stretch, and the end of the stretch. And here the preference was given to the flexible payment because it has a tendency to deteriorate fast. On the collected soil samples, we have performed several tests like density test, specific gravity test, Atterberg limit test, and UPV test. Figure shows the ultrasonic wave velocity setup where the velocity wave were passed to the soil samples and it affects the density and the elasticity of the soil. Further, to combine our UPV test result with the real-time vibrational data of the road surface caused by the vehicle movement, and Anuro-Udo acceleration-based sensor, which is a low-cost sensor and easy-to-use sensor, which was connected to Swift vehicles, and the speed limit was skipped to 10 to 20 km per hour restricted, and with the constant tire pressure in the second gear. And here the data was collected up to the 6 month, considering various environmental factors and payment load conditions. Then after the collected data, the further analysis was considered based on the 4-layer CNN networks, which predict the failure patterns. And the model is further analyzed by performing accuracy, precision, and evaluation to the payment failures conditions. Here, when we have the higher acceleration result, it indicates that the higher distress in the soil, and the CNN model further predict the failure patterns. Then after whether we get the UPV test result is accurate or not, then we perform the ANOVA test, and it gives the P value, and the P value is set if it is less than 0.05, then the results are accurate, otherwise it is not. So here some laboratory parameters are there for the key locations, and which further help us to analyze the weak potential point in the payment. These are the results we captured from the UPV test. Basically it gives the primary wave velocity and the CO wave velocity. Further using the Butt et al. Reference, dynamic modulus, CO modulus, and the Poisson's ratio were calculated. And it can be seen from the UPV test result that for the all location, the primary wave velocity, which was in the range of 150 to 300 meter per second, and CO wave velocity in all the 4 locations less than 180 meter per second, and suboptimal Poisson's ratio of less than 0.35, which indicate that the pavement are in the deteriorate conditions. And based on the modulus of elasticity, we can say that the location 1 and 2 having a fair conditions, and location 3 and 4 have bad condition, poor conditions. So further to capture, here figure shows the overall workflow of how to convert the acquired data from the sensor into a suitable parameters, like digital output into the acceleration and jerk and the velocity, the Z-score method, IQR method, and how to avoid the noise cancellation parameters. Those methods are performed. And based on the regression statistics data set, we can see the correlation between the sensor and the CO wave velocity, and all the values are closing to 1, which indicate that the model has a strong discriminatory power. And here the consistent trend in the actual versus predicted graph further validate the model. And here the CNN model achieved 92% of the accuracy. It also analyzed some false positive and false negative values, which may be because of some environmental factors and typical pavement failure conditions. Further to check various AI model techniques to predict the CO wave velocity was also analyzed, like exhibit methods, SVR methods, CNN method. Among them, we can say that the feed-forward neural network gives the highest R-square value with minimum error. So with this, I conclude that the study demonstrates that the potential use of the UPV test is a need of hour, and which can replace the traditional CBR and plate load test. And this particular proposed model is achieving 92% of the accuracy with correctly identifying 87% of the evaluated cases, and 15% of the predicted values are unexplained because of some environmental factors and some moisture levels variations. To further enhance the model's robustness, we can say that the study can be conducted for different geographic location, varying soil, taking in consideration of the various soil types and pavement patterns, traffic pavement patterns. These are the following reference.
Thank you, Jignashaji. So we can have the question and answer session at the end of the.
Okay.
The next presentation is machine learning methods to predict ballast breakage in railway tracks. Any of the presenters? Then use of machine learning for granular geomaterials, a short critical review. They have set it to 10 minutes. They set it to 10 minutes there. Yeah, that's it. Yeah.
Hey everyone, I'm Hayden. I'm the one in the blue bold letters. So I'm a PhD student at the University of Technology, Sydney. And together with my supervisors and Richard Kelly from SMEC in Australia, I'll be presenting a short critical review on the use of machine learning for granular geomaterials. Since this is about a 7-minute or so talk, emphasis is on short. So just as a brief little introduction, everyone knows, and we've seen from the presentations already, there's plenty of different machine learning algorithms, techniques, and so there's lots of review papers on those already. Okay, so I'm not going to be talking about the intricacies, everything like that. What I'll be focusing on is actually looking at the input parameters used and how they sort of adhere to geotechnical understanding. So the main focus will be on looking at the shear strength and the resilient modulus, okay? And classing between sort of two rough classifications, I'll be comparing conventional regression techniques as well as the more advanced machine learning techniques. So there's lots of models previously that have already been proposed in order to basically predict the shear strength, whether that's the outright shear strength or the friction angle or a variation of that, okay? So what you can see here, the common trend is they're generally as a function of the normal stress, okay? So that's derived from basically getting a relationship for the normal stress as a function of the failure envelope. Moving on, if we don't know what that normal stress actually is, we can ideally use some material parameters, material properties as input parameters instead, okay? So this is an example in the previous literature of using the median particle size, coefficient of uniformity, and relative density. But the issue with this is, even though they've said that there's a decent R-squared value of 0.7, if we look at the exponents, they're very, very small. So even if we have a variation in some of these parameters, there's not actually going to be much of a variation in the overall predicted shear strength value, okay? And that's where we see a lot of horizontal results, okay? So from that, one of my studies last year, I looked at, again, calculating the peak friction angle, but as a function of 5 different input parameters instead. And this was for a variety of material types, not just one type of sand, one type of gravel, okay? So using this, the results were pretty good in terms of predicting the peak friction angle for a variety of material types, but there is a noticeable scatter with the sand rubber materials, which are in the yellow on that screen. So basically, the regression techniques, because we have to assume an underlying nonlinear relationship already that we don't necessarily know, and the overall technique is quite basic, we struggle to inherently capture what is actually happening with these materials, okay? And the other thing is we rely heavily on regression constants that we have to obtain from experimental methods anyway. So if we need to do that, why do we need machine learning anyway? So moving on to the more advanced machine learning techniques. Okay, this is probably, I'm sure everyone who's sitting here knows what artificial neural networks are. This is an example from about 10 years ago that was predicting the peak deviator stress from triaxial specimens for sand mixed with plastic strips. Again, the results are quite good. They got very, very high R-squared values, but if we have a look at the actual input parameters used, we've got the plastic content, the elongation of those strips at the failure, we've got the strain at the failure, the aspect ratio of those plastic strips, as well as the confining pressure. So there's no real key geotechnical parameters or information in that model which kind of hinders its generalization to be applied for different materials. So it's sort of a horses for courses scenario. In a similar manner, this study from about 13 years ago was predicting the triaxial axial stress strain curve. And again, if we have a look at the input parameters, we've got rubber content, rubber type, test type, because they have used different triaxial tests, axial strain, and confining pressure. There's no material properties, there's no other, say, material hardness, density, compaction, things like that to describe a more generalized material. So this would likely break down when using a different material under different sort of physical states. This one looks a bit better in terms of the geotechnical information included. So we've now got soil type, okay, which is the Unified Soil Classification System as an input. We've got a variety of different particle sizes, the gradation, as well as the relative density. But it does look a bit intense. There are a lot of degrees of freedom, but again, I'm not talking about those intricacies in this. So the other good thing about this model is it wasn't applied just for one sand specimen or one gravel specimen. We have a variety of different sands and gravels under different various gradations. And because that database had different material types, they were able to actually incorporate these parameters into their model. But one glaring sort of thing with this model is they're predicting the peak friction angle. We know that the peak friction angle is a stress-dependent parameter, especially for these granular materials where the failure envelope is quite non-linear, okay? But there's no stress parameter such as the confining pressure that's been included in this model. One last example is, again, from the paper in the bottom corner. When we've used a much simple artificial neural network model with 5 key parameters, we had pretty good results to predict the peak friction angle, but we found, much like the previous study on the previous slide, adding the coefficient of curvature, which was the gradation parameter, actually improved the generalization of the model. So there was better performance with respect to external validation data. I want to briefly touch on how we as machine learning geotechnical engineers actually validate our model. So this will be pretty brief in the interest of time, but generally the first 2 steps that we stop at are looking at an independent data set, getting statistical parameters, so R squared, root mean squared error, and also looking at the relative importance or the sensitivity of each parameter. In the current literature, there aren't as many studies that go to this 3rd step of actually looking at how the model behaves with small changes to each parameter. And this step here is what I believe that we need to do a bit more as geotechnical engineers in order to bridge the gap between machine learning and industry's hesitancy to use machine learning. At least if we can do this extra step, we can validate our models that they behave according to the behavior that we expect, not just an overfitted model. All right, I'm going to race through this because I'm running out of time. The last section that I want to talk about is the resilient modulus. Hopefully a lot of people here attended Professor Indraratne's presentation. He spoke about why the resilient modulus is important, especially for railway track substructure. If you aren't aware, it is basically
1 minute.
The stiffness, the ratio of, or it's the stiffness for the recovered part under cyclic loading. Okay, so the simplest model that we have, which is quite often used in Australian track design, is just multiply the California bearing ratio by 10. But that has its own problems, and there are wild, massive inconsistencies with that. The other common way is to use the K theta model, or a variation of that, which uses the bulk stress, which is the sum of the principal stresses. Again, common themes are they're generally suited, so we generally have one model for each individual material type or loading conditions, so we might have 10 different coefficients for each model, and how do we know which one to use? In terms of machine learning or advanced machine learning, there aren't as many advanced techniques applied for coarse granular materials. The majority of it is for softer and fine-grained soils. But quickly racing through 2 examples in the literature, again, we can see that although they include some geotechnical parameters, we're missing out on particle size, gradation, density, loading frequency, and all of this. So just to conclude, I'd like to say that we can see from this presentation and every other presentation, using more advanced techniques, we're able to incorporate more geotechnical parameters that are otherwise difficult with conventional regression techniques. But there is a clear divide between studies that just fit a specific set of data or studies that develop more generalized, robust tools in order for practical use and viability. Lastly, data scarcity is a common thing that's said in many, many machine learning studies, and I want to encourage those who are doing more laboratory testing means to publish more material property data so that we can use them in our models to increase that generalization. Thank you.
Thank you, Hunt. Now the next presentation is bearing capacity factor prediction of strip footing on a spatially varying slope using surrogate model. Nobody is there, no? I think they are not there. Okay, we'll call this a next class.
Good afternoon, everyone. I am Priyanka Sharma. I am a PhD student from CSIR Central Building Research Institute. So for today's presentation, my topic is bearing capacity factor prediction of strip footing on spatially varying slope using surrogate models. So let me start with the outline for today's presentation. We change it. Yeah, I'm pressing green. Can someone help me? So this is the outline for today's presentation. I'll start with the need for this topic, whichever I have selected, followed by the problem statement, which I considered for this study, followed by the methodology, the results, the conclusion, and the references. So when we start talking about the foundation engineering actually has reached far away due to its advancement and the demands we had for whatever kind of needs we are having right now in the world. So there having been more complexities in the scenarios, the foundations designs have been more complex, and due to this, whenever we are doing any designing, it has become a very time-taking process for all of us to design any kind of foundations. So another aspect is when we are moving towards a more realistic perspective of designing any foundations, there comes the picture of uncertainty. And this uncertainty can be found in terms of like load conditions, or majorly if we talk about the soil spatial variability, which is one of the vital source of uncertainty when we like study any particular soil domain. So it is very much important to incorporate this soil spatial variability. And mainly, again, if we talk about any site-specific conditions, there are other conditions other than this spatial variability, if we want to talk, is the non-stationary conditions. When we go through the in-situ measurements, which we find from the fields, it has been very much clear that the variability, along with this variability, the mean or the standard deviation value of any like strength parameter, how it is going to vary along the depth. So that is one of the important perspective that we need to incorporate along with the this foundation designs. So for that we move towards the probabilistic aspect and the probabilistic approach, which makes our foundation design and the safety factors which we consider more towards the realistic conditions. So this probabilistic approach actually takes too much of time for the numerical analysis. It becomes a very time-taking process, since other than simply designing a foundation on factors like loads, there can be complex cases where there can be combination of loads. So it becomes much more complex. And if we talk about a horizontal ground and a slopey ground, it becomes, when we talk about slopes, there comes another crucial factor and it becomes more complex. So in total, the complexity increases and the computationally it becomes very inefficient, and an expensive analysis comes out. And because of this, it becomes a very time-taking process overall. So there is a requirement of this computational efficient approaches. So there comes into picture these surrogate models, and we are now moving towards a computationally efficient approach through these surrogate models. So I have considered a simple problem of a vertical load on a spatially varying slope condition along with the non-stationary characteristics into that. So this is the schematic diagram of my slope footing system, and I considered a 2-meter strip footing, and this slope angle was 30 degree, and overall the height of the slope was 10 meters. And on the right-hand side, this is a representation of the non-stationary characteristics along with the depth, how exactly these, along with the depth, the like strength parameters can change with its mean or with its standard deviation value. So this on the extreme right corner is a typical realization of this non-stationary random field, and this has been generated through OptumG2 software with the MATLAB interface for this analysis. These are certain parameters which has been used in this study. The mean undrained shear strength parameter has been used here, and which has been changed for the uncertainty conditions, and the random field has been generated based on that. So the probabilistic analysis, if we go on for that, there should be some like initial study on the convergence so that we can fix the number of simulations which we need to actually do. So for that, we did the convergence study here. This is the plot for number of MCS runs with respect to the mean bearing capacity factor, and we could found that almost for 500 a number of MCS runs, our analysis was like truly converged. So we have created certain MATLAB script initially to generate the random fields. So these random fields were generated using KL expansion method. This KL expansion method basically is a spectral expansion method which we normally use to decompose this the covariance matrices which we generate for these random fields. So overall this analysis, the computational time it took was for 500 MCS simulations was around 29 hours, and it was like too much. Even if we have used a very much like good like specification workstation, still it has taken like longer time of 29 hours. So we moved towards a methodology for developing surrogate models for this particular problem. We started with the geometric creation, in which we initially have imported the slope coordinates from the OptumG2 software, and then we have defined the slope domain in the MATLAB script. Next we move towards the grid generations, in which we have created this grids through this mesh grid. In mesh grid is a particular function which we can use to form a rectilinear grid, and then we store the X and Y like arrays followed by a covariance matrix through which we are going to basically generate our random models, and the KL expansion method was used for decomposition of this covariance matrix. So finally, after this random field generation was done, the values needs to be extracted. So there was another step. We knew that since we are working on this on a domain which could be very large, and the number of random variables in that random field, it can be huge in number. So how do we try to reduce that? So we have put one condition of the KL terms in that. So we try to make it.
You have to speed up.
Sorry. Okay. Sorry. We tried to like select those. We had made a threshold like percentage, like above 95% of the energy terms we have considered into our SPC model. So the next like step was integrating this by mapping the random fields into the OptumG2, and finally the analysis was run and the results were obtained. So in the right-hand side, this is the overall methodology which we have used. So random field generation, already I have explained it. Next, what we did, we went to the generation of the initial experimental design to form this set, which we fed to a PCE model, that is polynomial chaos expansion surrogate model. We have built it, and we have fed the whatever sample set we have generated. Other than that, what we did to reduce the computational time more, we have generated one sparse SPCE model using this sample set, And then we have predicted some responses, and we tried to check, like on the test data, how much accuracy we are getting. So we fixed that if the testing accuracy is greater than 95%, we are going to follow follow it and consider it as a final SPCE model. Otherwise, we would increase the number of candidates set, and again we will follow this whole chain. So other than that, there were two aspects. One, since we have obtained this final SPCE model, it can be run and we can obtain the response out of it. Our response is the bearing capacity factor. But other than that, in order to make it more like a computationally reduced model, we had again worked on the global sensitivity analysis through Sobol Index 1. So this is the flow chart for that. So these are some of the results. I will be very quick due to shortage of time. Sorry. Okay. So these were the results which we obtained from the full SPC model versus the reduced SPC model. The reduced one is through the GSA-based SPC model, basically. So the results, we could find that for a training set of 128 samples for the full model, the R-square value was 0.97, and for the reduced one, it was 0.9561. So these were the satisfactory results we obtained for using just 128 training samples. So these are some of the conclusions drawn from my study, that the combination of SPC surrogate model with the global sensitivity analysis, it proved to be very effective for predicting the bearing capacity factor, and the reduced number of KL terms that has been used here, it could help to train the SPC model with greater computational efficiency. Other than that, we could see that only with using this 128 number of training samples, there were satisfactory performance results from this SPCE model for both the full as well as the reduced SPCE model. And the time, whatever our main focus was on computational time, we could see that the computational time was reduced to approximately 25% of the original time required for the numerical simulations. So this could actually reduce the computational burden which we have on the probabilistic analysis of any complex foundation problems more feasibly. So these are my references. Thank you, and I would like to acknowledge my institute for allowing me to come here and present this work, and I'll be happy to answer any of your questions.
Thanks. Maybe questions can be followed later. Next presentation is machine learning based studies on settlement characteristics of soft clay soils. Saurav Chaudhary, Ganesh and Burana. Anyone is there? Okay. Now comes to the last one, a comparative study of ANN models for the prediction of soil compaction parameters. Harish and Netra.
Good afternoon, everyone. I'm Harish from AME University. I'm a PhD third year student, and I did this research with my professor supervisor, Netra Prakash Bandari. And today, the topic is the comparative study of ANN models for the prediction of soil compaction parameters using routinely tested soil properties. And starting with the introduction, and in the slide, we can see a graph, which is called moisture density curve. And this curve is required to get soil compaction parameters, optimum moisture content, and maximum dry unit weight. But to develop this curve, we need at least 4 to 5 test points. So that's what makes this curve, or this test, a time and labor intensive testing. So this motivated many researchers to do the research to develop a predict model using the soil properties which are routinely tested, such as Atterberg's limit, radiation parameters, specific gravity, and properties which reflects on the mineralogical composition of the soil. And this figure summarizes all the research has done so far on the predictive modeling of soil compaction parameters. the machine learning and artificial neural network, which have been developed to predict the soil compaction parameters, use manual design, which is subjective, time-consuming, and sometimes have a risk of overfitting as well. So for a beginner like me, when I was starting to learn about the coding, I didn't know much about the computer coding. So for people like us, purely geotechnical, there should be a model which can make a predictive model when you give the hyperparameter ranges, evaluation metrics, and how to search it. So I found that there are methods which are called automated ML, and so this motivated me to do this study. And for this study, I used neural architecture search, which has shown some great results in other fields, but has limited use in geotechnical lab test data prediction. And these are the objective of our study we conducted. And for this, we prepared an architecture using neural architecture search. And then we used two models. One is resource efficient search strategy, and other is surrogate guided search strategy. So we compared the results of these two techniques, and we presented our results here. So for database, we created a database collected from more than 14 studies given in the figure, and the general descriptive statistic of the soil data we collected is presented in the table in the slide. And we did the correlation test, and we found that the optimum moisture content and the maximum dry unit weight are strongly correlated with the routinely tested soil properties such as liquid limit, plastic limit, group index, and clay fraction. But the problem is these some pairs of these soil parameters such as liquid limit and plastic limit, plasticity index and group index, these are highly correlated with each other as well. So that gave me a moment to think about some method which I can apply to decorrelate them so that the effect of multicollinearity is minimized in our final model. So after data compilation, we did the data pre-processing. In the data pre-processing, we started with the transformation to reduce the tail dominance. And the figure shows that after transformation, the tail dominance have been significantly reduced. And this is the particular example for sand content only. We saw the same kind of results in other soil parameters as well. Later, we did the scaling of raw data to normalize the spread. And finally, what we did was principal component analysis to reduce the collinearity between the parameters. So we kept the components which could explain 95% of variance for our data set. We kept those. And this not only reduces the effect of multicollinearity, but also reduces the complexity of a model. So we retained the 5 components of principal component analysis. After that, we went through the building of ANN architecture for our model, and we used neural architecture search. And what it is basically a combination of search space, search strategy, and evaluation metrics. Search space is defined for the width, depth, and connection of the ANN architecture. Search strategy is the algorithm used to tune the model between the ranges of these width and depth parameters. And evaluation metrics was used to evaluate the candidate architecture which were found during the tuning process. And these are the values and ranges of hyperparameters we used for the search space. And then search strategy. We are comparing these two search strategies, hyperband optimization and Bayesian optimization. Hyperband optimization is based on the early pruning algorithm, and Bayesian optimization is based on the surrogate guided. And the first one, we can call it resource efficient NAS, and the second one, we call it surrogate guided search strategy. And finally, the evaluation metrics, we used Hoover loss in combination with the coefficient of determination, coefficient of correlation, mean squared error, root mean squared error, mean absolute error, and weighted mean percentage error. And we named the model after the search strategies they employed. So for model 1 is the model using the hyperband optimization, and the model 2 is the model using the Bayesian optimization algorithm. So in the results, first the principal component analysis. So these are the inputs, so the first part of our analysis. And we kept the 5 components of the analysis to explain the 95% of variance in our data set. So the PC1 explained the most of it, then the least one describing component was PC5. And these are calculated based on the contribution of each soil parameters, the routinely test soil parameters. And the contribution is shown through the heat map given beside the cumulative variance curve. So this table shows the final tuned architecture of our ANN model. Both the model converged on the same activation function and optimizer. The learning rate was no different. There was marginal difference, but the main difference was found on the width and depth of the layers. And we can see that hyperband optimization model used the deeper 3-layer ANN, while Bayesian optimization used the 2-layer ANN. So what this tells is the resource efficient NAS just ignores the architecture which are not performing well at the start. So the late bloomers are just removed from the tuning processes. While surrogate guided, it develops a 3D statistical model, and based on which it selects the candidate ANN model which will perform well, which has a tendency to perform well. So we get a more generalized, more accurate model in Bayesian optimization. But the thing is, hyperband takes less resources, less time.
1 minute more.
While
1 minute.
Oh, okay. Bayesian does a detailed analysis and gets the more generalized model. And these are the performance metrics, and in every metrics, Bayesian optimized the model has won. And even for target variables, we did the point-to-point plot. And the Bayesian, when you plot the train and test data in the one actual versus predicted plot, then the data are hugging the 1:1 line. That is what we need for better generalization. And the story is same for maximum dry unit weight as well. So the Bayesian optimized model were able to generalize better than the hyperband optimized model. So lastly, to conclude, so NAS is a hands-off method of ANN design. So even if you don't know much about coding and only knows the fundamental of coding, then you can do the design or predictive modeling by yourself without depending on other. And target behavior was found, like the maximum dry unit weight had smaller errors, but the thing was the OMC was explained better in all the models than the maximum dry unit weight. And last but not the least, the search strategy really matters, and Bayesian optimization in all metrics was better than hyperband optimization. And talking about the limitation, the thing is we used principal component analysis, so we can't interpret the model. So that's the problem with this model, and further works are application of NAS for prediction of other soil parameters such as strength, settlement, and permeability, exploring larger search space and strategies. Thank you.
Thank you, Mr. Harish. Maybe now that we have about 6 minutes, we can have 2-3 questions from the audience. Okay, if there are no questions from the audience, I have a question. Professor Somai can answer. Now that see, most of the studies are in the academic institutions, we were thinking of about predicting the parameters for design, but we need to think of something for the performance and end life of the geotechnical structures. So what is that we can go about in using AI for such events?
No, when you are predicting some parameters, for example, water depth or anything, then you should do some cross-checking also. So, for example, when you are doing for site characterization, for example, you have a 500 acres land. So, what we do generally, we do perform CPT, some of the tests we do, because we cannot do the test all over the points. So, what you do, you try to develop the model, whatever data you have, and then you try to predict the data for some point where you have not done the test. And then we cross-check with the model and see the variation, how much variation is there. If that is acceptable limit, then you can go for the model. That is one of the cost validation generally we can approach. Second thing, you can do something, if you can add some Monte Carlo simulation with this. For example, if you try to generate some of the more samples by developed model, and then maybe we can go for the probabilistic approach, that is the possible. But this is the two approach. First approach is very useful nowadays. So they are doing also, you do some test, you develop the model, you do some test, and the test data, whatever you are getting, that you put in a model. So you have the experimental result. Now you can cross-check that how your model is giving. So in this way you can get the, verify your model actually.
Thank you. Now I request my co-chair to come. Thank you all for finishing in time.
Thanks all for the presentations. Actually today the total there were 5 presentations, and starting with the thematic lecture from Professor Samoe. After that 5 presentations were there, and most of the sessions were within time. So thanks for that. So formally, this is the end of the day 4 and Geotech Asia. So thanks all organizers and thanks Chair.
Thank you.
Thank you, everyone. I would like to request Dr. Jigisha Vashi, who is Joint Organizing Secretary of Geotech Asia Conference, to hand over memento to our chair, Dr. Raghuveer Rao. I would like to request Dr. Kshitija Nodgoda, Finance Committee Geotech Asia Conference, to hand over memento to Engineer Govind Raj. Thank you. Thank you, everyone. We are closing this session now. Thank you.